Yeah, thank you. Yeah, before I jump in here, towards Brandon's comments on NHD plus, I was involved for many years up there in the efforts for NHD. I will say that something to look at towards is the USGS climate centers. I know that a number of them are trying to come up with national data sets and analysis to help with climate change and other types of considerations. Currently, they're modeling over 250 different select species from the different states to look at distribution models, and are looking to incorporate watersheds, water resource type of information into NHD plus as well. And I'm sure that'll be, if not already considered up in Alaska, will start to be over the coming years. So, so Heather had asked me to take on this talk, which is a little bit of a grab bag of different types of considerations that was a bit hard to fit in other places in the workshop, and also kind of are unique to some things in Alaska, but also some things that are that we experience in many other places as well. So everything from looking at a little bit on geotechnical investigations, different types of environments, habitat features, and giant wetlands and how you cross them and size things, and looking at the synthetic width method within our Fish and Wildlife guidelines. And that's kind of an overview of what this will be about. The first one is when to do a geotechnical investigation. So we wanted to hit on this a little bit at a high scale, and because sometimes it's one of those things that, well, maybe we don't have to do that. We can take that cost off the list, and we just want to be able to point out here, it's not a when do you do it, it's rather a how. There's always a geotechnical investigation when digging into some type of road crossing. Looking at and some of those aspects are looking at the geology, geomorphology of the site, history replacements in the area, size or types of structures, what's the ADT of the road that you're working on. Some roads have higher standards than others that you need to meet. And then dealing with your little level of risk. And everything can happen here, from a desktop evaluation to augering and boring. And all of these are applicable depending on the size of your structure, the type of structure, the soils that you find yourself in. And back again, you're really controlling that level of risk. You don't want to be out there with the contractor and suddenly come across a giant fine bedrock a foot higher than you thought it would be, or a bunch of wet peat that you can't, that your footer's sinking in, when you could have solved that issue by doing trying to get at least one hole in the ground in that area. And then I only had one other slide here in terms of what some of the differences. Bottom culverts, you can say, are the culverts that are round pipes, squash pipes, arch pipes, those types of situations. Think of these things, think of anything sitting on the ground as floating on jelly or some other aspect than hard ground. And that's kind of how to look at this from that perspective, is they are floating within that soil and having to deal with the weights that are on top of them. And when you have a bottom culvert, it's one large footer. So here you have a 5-foot round pipe. Well, that has a lot of floatability on the soils below it than on the right, bottomless culvert, because those footers are only 1.5 feet wide. And of course they go all the way up and down the culvert, but there's less area there. And so you have to look at those soils more in depth and do a deeper or more focused geotechnical investigation to find out what is there. So that's all we wanted to point out here when doing a geotechnical investigation. They are necessary. The level of detail is something that an engineer would need to evaluate, talk about for the type of place you're talking. Sills is something that's come up off and on over the years in Alaska. They're not used that often in general across the state. I think I have seen them pretty much only used and constructed in two types of situations. One where there are sand-bedded systems, such as Gray's Creek here, which is on the Parks Highway. This was a DOT project back over a decade ago, and it's a sand-bedded system. There's no gravel in it, and so they put these sills in order to try to have some material coming from the falling limb of the floods and try to capture at least some sand and keep that in the culvert. It's very hard to put in rock in these sand bedded systems and hope that they stay in place, although it is possible in some ways, but you run the risk of some degradation on the downstream side if you put too hard and hard material within them. So one of the things to note here is that it definitely is, is not embedded that far. That would be my only issue with this one. So a lot of people tend to use these as retention, trying to retain sediment. That's not the purpose here. Federal highways actually, I think Heather and I were looking where they say they should not be relied on to retain beds. However, another place that I have seen them work, people have put them in is to help with making nice footers for step pools and cascades in those high gradient arenas. And even though you're designing the rock to stay stable in a 100-year event in a very high sloped environment, sometimes you want that little extra anchor at the downstream foot. And so those are the two places I've really seen those play out overall. So these things are not baffles. Baffles are a metal weir and a pool behind it, and they are sealed at the bottom. And so a fish jumps over the metal weir and gets to rest in the pool and then continues on. These are just to retain some bed at the end, receding limbs. And so that's why they tend to be, only half the depth of a bed. So that was another thing that kind of had a hard time fitting into different areas of this multi-day event. The next few slides, we're going to talk about incorporating habitat features and into these structures. And the one I'm going to start out with first, we're going to go from riffle pools, riffles to step pool environments, and then talk about habitat rocks in general. Riffle pools, we do not recommend. In trying to look at a reference system, and you've got this small creek and it meanders really nicely, has pools and riffles, and you're like, well, I want to try to make those within the culvert itself. Well, they don't really pan out in a culvert. Maybe ideally your culvert would be the length of your culvert would be kind of within the length range of a normal riffle within that system, and you can make the entire thing a riffle. But if you're looking at it and the length of your culvert has pools and riffles in the same length within your reference reach, we still don't recommend that because they tend to fill. The pools tend to fill over time. You don't have a floodplain within that culvert to any extent. And you don't have your meanders. You're not able to meander it enough that your scour forces maintain that pool over time. You need some pretty good meanders to maintain pools, and you just can't get that no matter how wide you make these culverts for the most part. So full riffle is the best option with these low flow cases, and especially using low forcing features for low flow environments. And we did do a test case of this once back 15 or more years ago, Edgerton Parks Road and Elk Creek in the Matsu. And it was extremely difficult to get the slopes right with the contractor. And it did over time flatten out. The pools filled up. It's still viable, but for the amount of effort and work that was involved with it, it wasn't worth it. And it also kind of shallowed up those pools. And luckily, we have a pretty good low flow going through there in a typical year. Next couple of slides are looking at riffles. And so there's a couple ways to look at what I would think of in thinking of habitat features. So we're all talking about low flow channel and how important it is. And many times you're looking at a single thread low flow channel, which is on the left here. This is an example of Murphy Road. And especially with small creeks, and knowing that things get pretty low flow in the middle of summer or so, you want to concentrate all that flow into so that you have one low flow channel when it gets to that. This is a bankful wide culvert, and so the water is running through that low flow channel in the middle of summer right now. So I guess the low flow itself, the feature of the low flow is a habitat feature. Sometimes you can get away with things like Schwald Road on the right, which is a spring-fed system. There's not much sediment coming down. It's a very stable flow from the spring. And then you can think of things that looking at a kind of a rougher riffle and breaking that low flow up into various components going through there. Lots of hidey holes for fish, lots of ways that fish can get up through there. But it's a very consistent flow. And so you don't necessarily need that one low flow environment for that type of situation necessarily, although it wouldn't be bad we're having that as well. Overall, these riffles are the most stable option in general for geomorphic designs. And the other piece of the riffles when thinking about habitat features is, and looking at low flow, is how you keep that low flow concentrated and that low flow channel maintained over time. You can do things like riffle rock bands or riffle rock clusters. These are bankful wide channels here. And on the left at Meadow Creek Loop, you can see that this is middle of summer. It's July 25th, way too far in the past for my preference in 2004, but this is low flow going through there. And that rock band, there's I think three of those in that culvert, and it has a low dip in it. And that's what helps keep that low flow moving through there and keep that channel stable in the low flow condition over time. In Diamond Hook, there is, these are clusters, and you can even use rock bands with clusters. And this has a pretty significant low flow channel that is almost a foot high. And so these help maintain that over time. Little Campbell Creek varies quite dramatically in terms of the flows that it experiences. And so these things get to be pretty dramatic in how they look. On the bottom here, the Forest Service has a few guidelines for rock band spacing and for rock clusters to kind of keep them out of the issues of the inlet and outlet, looking at the various velocities at those places, but also how much you need to keep things maintained over the years. When we talk then and moving steeper, we're looking at step pools. And so with rocky riffles, you can consider them all the way from 0 up to 6% slopes or so. And then it becomes more of a cascade system, which is an even rocky ramp in some ways. But step pools are present in a very specific slope range within the geomorphic environment. And so if you're going to do these, we have a few qualifiers with them. They can be a little less stable if you don't construct them correctly. You have to look at the step differences. You can see some of the qualities of step difference that we use in the Matsu for salmonids. And then, and we recommend these for larger streams, probably 15 or wider. For smaller streams, it just gets a little tough. You want to be able to use the 3-foot diameter rock or bigger for these steps so they don't move around. You don't have kids coming and trying to move the rocks, which we do in rural urban environments, and that sort of thing. When we look at designs for these, this is a very typical thing we watch out for is, what constitutes the pool. So on the left, where you look at step difference and the pool depth, that's what you want to look at. You want to be careful of a designer looking at their 1-foot pool depth being the middle one that's X'd out. This is an example of a step pool. It's Government Creek, and you can look at the upstream reference here. You can look at what was there before we replaced it. You can look at the larger steps that were made. And then 10, 12 years later, you can see that while a few of the rocks in these steps have moved around a bit, they are actually still a viable step pool system. So these things can work. Again, this is a bit larger system. It's about 16 feet wide creek here. That leaves us with habitat rocks. And so the drawing on the right kind of shows the spacing of some habitat rocks in this culvert. And when we think of this, I've last 6 years, I've done a lot of work with rocky ramps in stream restoration. And there we use habitat rocks if we cannot get the velocities correct to get our target fish up above, up through a ramp. But in a culvert, you can do the same, but we have to be careful of that. More rocks for fish doesn't always correlate to more fish passage or a better culvert or a geomorphic culvert. So some thoughts here is that you want to emulate what's in your reference reach in terms of woody debris and boulders, random boulders that are just super large and sticking out of the water. You can emulate their cadence and amount within the culvert by emulating that reference. But when there isn't any of that and you still want to put habitat rocks on, then you look at restoration literature. And these are three places for that literature. These are some of the points I make in rocky ramps, and I think they apply pretty good in these culvert environments as well. You don't want so many rocks that you're blocking your bankful flow coming down and messing with that continuity of flow at the bankful event, or not putting these boulders so close to your edges that you're starting to scour your stream bank out that you spent so much time putting in your channel in the culvert. Some of these things which are good to note. And so these are in here for reference if you do end up wanting to put habitat rocks in your culvert. And again, we're going with a geomorphic approach. And so we don't need, if you do that, we don't necessarily need to put in rocks so that fish can swim and burst speed between one rock to the next in order to get up through here. They should be able to do that just fine without them. Especially with habitat rocks, one thing to look at here is the concept of the scour. You've got this habitat rock or some type of rock sitting here on the top, in the water will run over it and scour behind it, the smaller material, and then it rolls. And that is what happens, how bigger rocks roll down a creek. But some options to decrease this are putting in footers, whether it's two small rocks, a large rock underneath the rock, or just one big rock to accomplish the entire thing. Any of these work, and footers are a key element if you're going to put in rocks that aren't locked into other places in order to keep them stable over time. And that is something that we find all the time, is putting these footer rocks are really something that's missed, and contractors don't like to do it. Designers leave it out. Something that you really need if you're going to put these rocks in by themselves. So now we're going to talk about off ice and permafrost environments for a few slides. Then we're going to get into some wetland environments. For off ice, I really like, there was a paper that Doug King did in the 80s, looking at how the process of off ice formation. Basically, you have a gaining reach of a creek where groundwater is naturally flowing into the stream, and it gets frozen over in the winter. Then the pressure of that pushes that ice up. It breaks, water comes over the top, it freezes again, pressure, break, freeze. And that is successfully done over the winter months. Some places are worse than others, but it is a natural event, and it's groundwater driven. So what do we do if we got these issues? I mean, we have issues like this all over the state, off ice. And, sometimes, the recommendation is just to avoid these really bad-ish places, but with roads, that's not always the case. So what can you do? If it's over widened, you can bring it back to your dimension plan form. But you might still get icing, but because your vegetation hasn't been established yet. This was the case at Cardiff and Lupin on the left in 2005. We brought a 3-foot stream from a 30-foot wide from a lot of trucks going through it to back to its original dimensions. However, the vegetation took time to develop, and so it would still ice over and cause off ice issues. Now, when the vegetation came, the willows came on and made a little bit of heat blanket over the creek. That's all it took. So this does not ice over anymore. A wider culvert is not necessarily better, or it is not a solution. It can help a little bit, but it's not a capacity issue. This off ice formation, it's a different animal, and it'll still be bad if it's in a bad area. One of the other aspects of off ice is fish passage in the middle of summer. Here on the right is a culvert in the middle of the Kenai Peninsula, where, here we are in June or so, and you still got this giant block in there blocking fish passage. So it's something that we need to consider and account for in some ways. What would help here is probably a nice little low flow channel underneath this that can concentrate some of the heat and have a little opening down at the bottom of this ice as it's melting. Some of the consequences, of course, are you can mess your ends up pretty bad. You can have sediment uplift, and things can be blocked into June or later. Especially bad up on the north slope in places as well. Some of these things, other things to do are thaw pipes. That's why you see these things, so that people, maintenance folks, once off ice gets too bad and is threatening the road, they can get in there and throw some heat down in there, that they can try to get these things open. They can, here's Alaska DOT just ripping out a bunch of this stuff so that they can at least get some capacity. You can keep your pipe skew, not skew it across the road severely. That helps. You can upsize your culverts, you can deepen your channels. You can even do things like, put concrete head walls on your outlet and inlet in order to keep them from getting damaged. So lots of options for off ice mitigation, but it's mitigation. It's not necessarily the entire solution in every case. Transition from off ice to the periglacial zone or the Arctic. I like this because it's one of the only geomorphic documents out there that talk about the Arctic in terms, and this is in terms of the larger rivers, the periglacial river systems. But you can see here that's braided, and branching. There's a lot of sediment supply, not necessarily a lot of stream power. And so you get a lot of braided systems as you move further north. Some of these aren't able to have bridges on them. And so you end up crossing braided systems with culverts on the road. And then you have other issues with that when you cannot cross these from bank to bank. Also, there are the hydrology is irregular. There's sudden fluctuations. It can be dry sometimes. It's as in many parts of the state, there can be often underestimation of the flood flows, and there are interesting things you only find in the Arctic, like these beaded streams. These between the lake systems are these really narrow e-channels that are only a few feet wide and 3 or 4 times the depth of that. And how do you cross these things in a permafrost environment without starting to cause permafrost degradation? It's a real question. We have, again, some of the same things as off ice formations. We have deformations, seam failures, perched inlets and outlets. Lots of things going on with these things. Some of the mitigations, again, same things. End restraints, you can see a nice concrete head wall here that's protecting the outlet of this culvert, using very heavy gauge pipe, trying to avoid locations where possible. And then insulation. So here's DOT putting an insulation in on top of the bedding before you put the culvert in order to try to keep the permafrost stable underneath it and hopefully reduce that off ice and other deformation potentials with permafrost. So some unique aspects here, definitely in the Arctic to consider that we don't need to in other places. Now I'm going to, so the challenge is figuring out how to transition, but I want to do a bit of a 180 and go to the tidal areas. As we go to tidal, we can look at how do we get fish passage through tidal areas. There are only a few of these out there in Alaska now. It's not like the Pacific Northwest, where there's a lot of levees and a lot of tidal influenced culverts and that you have to deal with. We're relatively, it's a relatively good thing that we don't have a lot of these, but we do have a handful in the southeast and in south central, like this one in Chester Creek and Anchorage. And we have a bit of criteria. This is the same in the Fish and Wildlife Guidelines. It's the same criteria that we have in Anchorage and in the Matsu, which a lot of this research was based from Puget Sound and was tested out here in on the Chester Creek project back in the day. And basically, you want passage through your culvert 90% of the time of your average tidal cycle. So, you know, that doesn't mean you don't end up with the perch at some point. But 90% of the time, you either have flow through here or this whole culvert's backwatered and fish can kind of get up through there because there's really little velocity to prevent them from getting up through there. That's it in a nutshell when you talk about tidal influenced areas and criteria associated with that. One of the things that is interesting that I found is you can look at it in terms of a reference condition, which you could translate to more of a geomorphic condition. You can take a kind of more pristine tidal site and then compare it if you have an existing levee or culvert. You can look at those mean tidal ranges, map that through time, and kind of see, is your culvert too high, or are there other restrictions to that natural tidal event, and then be able to try to emulate that tidal event with where you place your new culvert. So something to think about if anybody ends up working on that sometime. Something with the real world benefit here. This is Kirsta with Cordova Watershed Project, looking at Odiak Pond in Cordova back about 8-10 years ago, looking at these 3 culverts, and you can do things like look at how long are these inundated and when, and which culvert, which of these culverts actually have that kind of backwatering over time, and use that in terms of saying, well, how much do we need, how much fish passage do we actually have here, and is it a problem? Lots of ways to use tidal information. Moving back from tides, looking at lakes, I think there was a question or two on lake outlets, or at least I think Heather brought lake outlets up a few times. Yes, back when we first started looking at these culverts and lake outlets, we wondered whether you really could emulate a lake outlet in general, and luckily the answer is yes, you can. In many places, as you think of a natural lake and an outlet into a stream, the lake shallows up, there's a shallow area, and then the outlet kind of hones into a natural dimension that the stream is going to be at. And so you can emulate this. This is an example from Engstrom Road on Cottonwood Creek Matsu. One of the things is, you want to design these with 100-year substrate stability. You're not getting any sediment coming through the lake, of course, in order to replenish anything within the culvert. Everything in the culvert has to be there when you construct it. And so you can see an example of how we're mixing that material. It looks very much like what Heather has been showing. A lot of fines in it, but a lot of large material too. And again, it's a well-graded material. We did put some habitat rocks in here because when you mixed all that up, it looked relatively uniform for some reason. And so we wanted to put some things in the low flow channel of this and provide a little bit of resting or break up the flow a little bit through that low flow. These things also help with predation. The theory being that if you're a small fish and you just have to be able to shoot through here, all the larger fish has to do is kind of wait at one end or the other or in the middle of the culvert. So you want a little bit of hiding areas for those fish. Another piece for the lake outlet to be a reminder of is we like have put in a little welded plate here. If for some reason all of this washes out and during a catastrophic event, at least we're not losing the entire lake in that process and having the lake level kind of be down here. Right? So it's a redundant safety factor. That is a good thing to have. Another good thing to have is a lot of shallow area that's helping hold the lake back. So all of this area here is also helping hold that lake back. And we just have a few nice redundant features here. So now we're on to wetland complexes. And so now we're spending the rest of the time on wetland complexes, relic channels, sloughs, and the synthetic width method, which is kind of like your last go-to at the end of the day if nothing else is working. For wetland complexes in the Fish and Wildlife Guidelines, we have method A and a method B. So we'll talk about method A first, because these complexes are challenging environments. Their flows can vary. Their bankful dimensions vary quite dramatically. I've got some good pictures of that. And when you think of using USGS equations or even gauge data from other watersheds, or even in some ways regional curves, something to think about is that usually these gauges and analysis are done on alluvial systems, not wetland systems, not systems that are only spring fed. And so these types of watersheds are really complicated to evaluate because the tools we have are for alluvial systems, not spring fed or not a system that is only wetlands in general. So it's something to think about when we look at this, and it kind of complicates looking at them. But if there is a reference, you can find upstream of your wetland complex area that is kind of ill-defined, as we see here in this figure 8. And you can see upstream here, we've got it is a single thread channel coming through the wetlands. Then that's what we recommend you starting with, and as your bankful width and getting and width and depth for that matter, in order to get the water through as your fish passes geomorphic flows. If you can't get that 100-year flow through the road, then you put in floodplain culverts, which we show on the right here. So you strive for that low to zero slope like that the wetland environment typically is. And you consider these floodplain culverts as needed. When we look at those some more, this is an old slide I had from previous workshops. You can see this nice single thread channel flowing down into Horseshoe Lake in the Matsu. So, you still have a variable width here, right? You've got water within these vegetation, so you're gonna have to make the best estimate you can. But these are really nice places to do work because there's so many juveniles in them, and they're almost zero slope anyway. There's no sediment transport. You can put these in. If you're putting and replacing an old culvert back from the day, a lot of times they fill this channel in with sediment, and then they stick a small culvert on top. And what's bad about this is off-ice issues, for one. This is a lot easier to freeze, having that little bit of depth compared to the real depth of the creek itself. And so we put these things and bed them down below the depth, natural depth of the creek. At times we've even just put pea gravel in these things, but we always make sure to put a good amount of larger cobbles in them in order, again, to help with predation potential issues. Moving on to relic channels and sloughs, these get complicated because sometimes it's worth a discussion. There's no straight answers. If we can look at on the left first, the relic channel. So Cottonwood Creek in Matsu used to be a large river in glacial times. Now it is solely a spring-fed system, has no connection to the Susitna Mountains, and its flows are far smaller than the large river banks that it has. And so it's been trying to make its own way all these thousands of years, but there's no sediment, so it's really tough. A lot of its meandering is because of vegetation growth over time, as you can see here. So when you look at this, where do you make your bankful call? The relic channel bankful doesn't, the flows don't exist anymore, yet it's still a wetted perimeter. And so, but then you got this little option A width there that is where the water's flowing. So it does get into a bit of a question. If you're thinking from a fish passage standpoint, your flows in option A probably do work. But if you're looking at it from a habitat standpoint, you may want to, if possible, if there's funding, if the biologists desire it, you may want to try to span that entire wetted perimeter there. Kind of depends on the goals of the project and what the goals basically are that everybody can agree to. But there are ways of doing this from a spring-fed system, looking at what is bankful for a spring-fed system, looking at some of these areas such as option A and kind of comparing that to the flow discharges and seeing is that now bankful or not. When we look at sloughs and braided systems, on the right here, you can see a meandering channel. Meandering channels then sometimes break off these meanders and they become sloughs. If there is more sediment than the water can handle, there will be an evolution to a braided system that you see here on the right. And the braided systems are as challenging as or more so as sloughs are. You still think of this wetted width concept. You have this wide slough, but all your conditioning of what constitutes a bankful and bankful discharge is embedded out here in the main channel. So it doesn't really apply in these environments. And so in these cases, you may end up thinking of the synthetic width method, which we'll be talking about shortly, in terms of how you can get something through that is different than trying to span the entire wetted width of this. In a braided system, the question is which of these braids do you add fish passage to if you cannot span this entire thing with a bridge? These braided channels move back and forth. The main flows go through various braids at different times of the year all the time. And so, it's probably worth trying to put a culvert in multiple of these, but is it all of them or some of them? It's a question that is worth a group discussion to figure out when you have one of these situations. I have no exact answer except to try to get a bridge across it, but that's not always possible. So that takes us to method B. Here we have an example of Nelson Road area, that road impounded. Well, it's not really a road impounded wetland. It is impounded to some degree, but would be a wetland at any rate anyway. So method B looks at a geomorphic classification, which you see on the left. This is Montgomery and Buffington's. I put in here kind of where rough and riffles can apply and where step pools can apply as a couple of options for the geomorphic classification or for the methods. But slope's really not, that slope's kind of straightforward, and the rough and riffle or step pool is pretty straightforward. It's really what kind of width you're trying to get to. And that's where this method tries to hone in on. So getting into that, you have this, say 500 feet of wetland. It's ambiguous. There is not really a channel except here at the road, but these road channels are pretty small. I don't know if that's really applicable or not. What width is going to be at the road crossing? You could say, well, I want the wetted perimeter. Well, that would be a 500-foot bridge. That'd be pretty tall order in this case. So what other options are available? I will say that this method does need further verification as we're going to get into it. But another thing here is a plug for gauging. I mean, even if you gauge only a couple years, you should be able to get a better idea of what bankful flows are in these environments over and above what the statistical USGS equations would tell you. And again, we're talking about bankful flow. And so that is the geomorphic linkage, is looking at a velocity that is related to bankful flow in the synthetic width method. Again, that's lower than the 2-year, but it's higher than the high fish passage flow. There's a lot of variable approaches to fish passage flow in Alaska. Usually 40% of the Q2 is used, but not all the time. But we're looking at bankful, and we're trying to link it back to a bankful geomorphic approach when we're trying to figure out how to get this thing across the road. So what we have in the guidelines currently is using a average velocity of bankful at 4 feet per second by Leopold. That's what he found in his studies over time in general. Now we have done some, Heather has some cross sections now of some more single thread channels in wetland environments that kind of show that 4.5 feet per second may be a little more applicable, but that work's currently ongoing. So this is a work in progress. What we do is then we take and base things on a bankful velocity, an average generic velocity, and stick the Manning's equation in it. So we put velocity here at B, we divide the A out, and we try to solve for iteratively all of these things, with being one of the variables within the hydraulic radius R. And we try to find out what that width would be. So some of the things we found so far with this method is usually your Manning's roughness coefficient should be around 0.03, which is kind of more of a cobble type of substrate, which makes sense. How many are, and then it's difficult to utilize slopes much higher than 1%, which also makes sense since you're in a wetland. Typically, they're pretty low sloped environments anyway. So there's been 4 places where we've been able to get some, try to verify this velocity, bankful velocity issue. These are graphed here compared to coho burst and prolonged speed velocities. And so basically we took those Heather definitely took those cross sections, calced out their velocities of those cross sections, which came out to be about, between 3.6 and 4.5. And at least each of those areas then used Forest Service, fish crossing methodologies from their analysis procedures in order to then look at what burst velocities at the inlet and outlet of a typical culvert or a prolonged velocity in the barrel would be based on a 40% of the estimated 2-year flow event. and how these compared. And so for at least for these 4 situations, they worked out that our bank velocities, if we used something between, that 4 or 4.5, it would result in fish passability. So that is it in a nutshell. Again, more verification needs and refinement is needed there, and things may help. These regional curves may help these cases, but these large wetland complexes and relic sloughs and channels are some of the more complex things to figure out because there really is no bankful feature to go by. And that's it.